Welcome back to educator.com. Today we're going to be continuing our study of linear algebra, and we're going to be discussing solutions of linear systems, part 1. This lesson is going to consist of a couple of very, very careful, systematic, slow examples of something called elimination in order to put a matrix into something called reduced row echelon form. So let's get started. So when we talked about linear systems earlier, we talked about the three things that we can do to a system of linear equations or a matrix, which is of course just a representation of that linear system. We can switch two rows, we can multiply one row by a constant, and we can add multiples of one row to another row. All of these three create an equivalent system, which just is our way of manipulating the linear system to make it easier for us to handle. Let's begin today's lesson by defining what we mean by reduced row echelon form, which is going to be the final form that we want to put a augmented matrix into. So again, an augmented matrix is just the system of linear equations, the coefficients of the linear system, plus that extra column, which is the solutions to that linear system. We're going to manipulate that, and we're going to put it into reduced row echelon form. So an m by n matrix is in reduced row echelon form. We'll often refer to it as just RRE. If the following holds, if all rows that are entirely zero, if there are any, are at the bottom of the matrix. As we read from left to right, the first non-zero entry in a row is a 1. We call that the leading entry. Has to be a 1. If rows I and I plus 1, so for example rows 3 and 4, if they both have leading entries, then the leading entry of the I plus 1 row is to the right of the leading entry of row I. So in other words, if I have two leading entries on row 3 and row 4, the one on row 4 is going to be to the right. It's not going to be right below it or to the left of it. All of this will make sense in just a moment when we give some examples of reduced row echelon form. Now, if a column actually contains a leading entry of some row, then all of the other entries in the column are 0. Note, a matrix in reduced row echelon form may not have any rows consisting of all zeros. So reduced row echelon form doesn't mean that we have to have a row that's all zeros. It means that if it does, they need to be at the bottom of the matrix. Okay, let's take a look at some examples. So we have the matrix 1, 0, 0, 4, 0, 1, 0, 5, 0, 0, 1, 2. This is in reduced row echelon form. Notice, this has a leading entry. It is a 1. Everything else is a 0. This column has, or this row has a leading entry, but notice it's to the right. That's what we meant by to the right. It's to the right of that one. And every other entry in that column is 0. Here, this row also has a leading entry. It is a 1. It is to the left of these other two, and every other entry in there is a 0, and it doesn't matter what this is. 4, 5, 2, this is not a leading entry. This is the leading entry of that row. These numbers they're not irrelevant, but as far as the definition of reduced row echelon, they're not important. Let's take a look at another matrix. 2, 1, 2, 0, 0, 2, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0. Same thing. We have a leading entry, zeros along the column. This one, notice this is a 2 here, and there's a 0, 0 here. There's the leading entry we haven't run across yet, so it's okay that this 2 is here. It has nothing to do with the definition. But now we run across, yes, the leading entry is a 1, 0, 0. It qualifies. It's to the right of this one. The next row, we have a 1, 0, 0, and it's to the right of these other two. So this one is in reduced row echelon form. C, we'll take 1, 0, 0, 3, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1. And we have a couple of rows of all zeros. So we have this nice big 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 5 by 5 matrix. Let's see. We have the 0 entries. They're at the bottom of the matrix. That takes care of part A of the definition. We have a leading entry in this row. It is a 1. That's nice. All of the other entries are 0. There's nothing in this column. Irrelevant. There is a leading entry in this row, and it is to the right of that one, and all of the other entries are 0. No leading entry, no leading entry, no leading entry. Yes, it satisfies the definition for a reduced row echelon. So these three matrices are examples of matrices that are in reduced row echelon form. Now let's take a look at A prime. 1, 2, 0, 4, 0, 0, 0, 0, 0, 0, 1, negative 3. This matrix, it has a leading entry, and other two entries are 0. But notice here, this row is the second row, and yet it's on top of a row that's not all zeros. So this one is not in reduced row echelon form because this 0 row needs to be at the bottom. Let's take B prime, 1, 0, 3, 4, 0, 2, minus 2, 5, 0, 0, 1, 2. Okay. In this particular case, we take a look at the 1. It's a 0 entry. The zeros are, the rest of the entries in the column are 0. Here, the leading entry, the first number that's non-zero, is a 2. It's not a 1. It has to be a 1 for it to be in reduced row echelon form. You can certainly take this entire row and divide it by 2 to get 1, negative 1, and 5 halves, and then you would almost be in reduced row echelon form. But as it stands, this is not reduced row echelon form. Let's take 1, 0, 3, 4, 0, 1, negative 2, 5. Let's take 0, 1, 2, 2, and let's take all zeros. Okay, so we have a leading entry, which is nice. All of the other entries are zeros, very good. We have a leading entry, which is a 1. It is to the left of, to the right of this one. It's the one above it is to the left of it. So far, so good. But this other entry here in this column is a 1. It's not a 0. It needs to be a 0. So as it stands, this one is not reduced row echelon form. Okay. Very, very important theorem. Every m by n matrix, is row equivalent to a unique matrix in reduced row echelon form, which means that no matter what m by n matrix I give you, with those three operations of exchanging rows, multiplying a row by a constant, non-zero constant, and multiplying a multiple of adding a multiple of one row to another row, with those three operations handled over and over and over again, you can convert it to a reduced row echelon matrix that is unique. That's what's really, really interesting. Later on, we'll talk about something called Gaussian elimination, and it's a slightly less detailed version of what it is that we're going to be doing today, and it usually suffices for most purposes in linear algebra, but the matrices that you end up with are not unique. What makes reduced row echelon fantastic is that even if you and your friend and another friend do a whole bunch of different operations, in the end, you'll end up with the same matrix. There's only one matrix that's in reduced row echelon form for any given matrix. That's actually kind of extraordinary when you think about it. So now we're going to go through a very systematic and careful example. We're not going to prove the uniqueness, but this example will actually show how you come across the how you transform a particular matrix into reduced row echelon form. Okay, so let's start off with our matrix. And again, I'm not going to be putting the brackets on there simply because there's a whole bunch of extra writing that we want to avoid. 0, 2, 3, negative 4, and 1. 0, 0, 2, 3, 4. 0, 0, 2, 3, 4. 2, 2, negative 5, 2, 4. 2, 2, negative 5, 2, and 4. Excuse me, my 4s sometimes look like 9s. And 2, 0, negative 6, 9, and 7. Okay, so this is the matrix we start off with. This is the one that we want to convert to reduced row echelon form. That's what we want. That's our goal. And we'll check to see that all of the properties of our RE are satisfied. Okay, so step 1. You want to identify the first column which is not all zeros. So in this case, we go here, reading from left to right, this column, right? 0, 0, 2, 2. It's the first column that are not all zeros. Okay. Again, very, very systematic. Step 2. Find the first non-zero entry in that column. By the way, this column is called the pivotal column. And the first entry that you find, which is right there, first column, it's the first entry going down that's non-zero. That's actually called the pivot. So in our first series of steps, 2 is our pivot. Okay. What we're going to do here is we're going to take this row, and we're going to interchange it with the first row. So we want the row that has the pivot in it to be on top. So I'll write out step 3 before I write the step 3. Interchange if necessary. You don't necessarily have to do this. In this case, we do have to. If necessary, the first row with the row containing the pivot. When we do that, we end up with the following matrix. 2, 2, negative 5, 2, 4, 0, 0, 2, 3, 4, 0, 2, 3, negative 4, 1, 2, 0, negative 6, 9, and 7. So all we've done is we've exchanged the first and third rows. That was the one with a pivot. We put it on top. Okay. Now we're going to divide this first row. So let's make step 4. Divide the first row, what is now the first row, not the original first row. So these steps refer to the matrix that I just completed. So divide the first row by its first entry. In other words, I'm just trying to make this first entry a 1. So I'm going to divide everything in this row by 2. So I end up with 1, 1, negative 5 halves, 1, 2, and then I copy the others. 0, 0, 2, 3, 4, 0, 2, 3, negative 4, 1, and 2, 0, negative 6, 9, and 7. So this is what I end up with. Okay. Next, I'm going to, actually let me rewrite what I had before. 1, 1, negative 5 halves, 1, 2, 0, 0, 2, 3, 4, 0, 2, 3, negative 4, 1, 2, 0, negative 6, 9, and 7. Okay. We are going to take our fifth step, and that is what we're going to do is we're going to, remember what we wanted to do, reduced row echelon form, we want to get all of these 0. So we're going to add a multiple of this to make this thing 0. In other words, we're going to multiply the first line by negative 2, add it to the fourth row, and see what we get. So step 5. Add negative 2 times first row to the fourth row. And then when we do that, so negative 2 times 1 is negative 2 plus 2, so I'll leave everything else the same. Nothing changes in the other rows. 2, 3, 4, 0, 2, 3, negative 4, 1. This becomes 0. Negative 2 times 1 is negative 2 plus 0. We end up with negative 2. Negative 2 times negative 5 halves is 5. 5 minus 6. 5 minus 6. Negative 1. Negative 2 times 1 is negative 2. Negative 2 plus 9, 7. Negative 2 times 2 is negative 4. Negative 4 plus 7 is 3. So look what we've done. We've created a row with a leading entry of 1. Everything else is 0. Now I'm going to put a little bracket here. My first row is done. Now I'm going to think about this matrix. I completely ignore this one. I never have to worry about the first row again. Now step 6. Well, this is the nice thing about it. We just repeat everything we just did. Repeat steps 1 to 5 for this particular matrix here. Okay? So what is it that we did? We found the first column that was not all zeros. This is all zeros, so we go to this column. And in this column, we find the first entry that is non-zero, which is 2. That's going to be our new pivot, okay? We take that pivot and we move it up to the top. And again, we don't touch this one. We leave it alone, so we exchange this row right here with this row. Now we're talking about 1, 2, 3, so we're going to exchange row 1 and 2. So now let's go ahead and write down that matrix that we get when we exchange row 1 and 2. Let me actually do a little arrow here. And I'm going to say switch 2 and 3. I'm sorry, so we're still talking about the entire matrix. So we're going to call this row 2. We're going to call this row 3. So we're going to switch 2 and 3. And when we do that, the matrix we end up with is the following. We get, of course, the original 1, 1, minus 5 halves, 1, 2. We get 0, 2, 3, negative 4, 1. We get 0, 0, 2, 3, 4. We get 0, negative 2, negative 1, 7, and 3. Okay, so now we want to take, remember what we did before, the next step, once we have this pivotal, the row with the pivot, I'll go ahead and circle the pivot so we know what we did to it. Now we want to go ahead and divide that by that number, everything in that row by that number, to turn this into a 1. So we will divide row 2 by 2, which is the pivot. The matrix we get is 1, 1, negative 5 halves, 1, 2, nothing changes, 0, 1, 3 halves, negative 2, and 1 half. right. And we get 0, 0, 2, 3, 4, 0, -2, -1, 7, and 3. So now we have a leading entry of 1. And now what we need to do is we need to get rid of did we make a mistake here? Let's see here. Let us multiply 2 times the second row, add it to this row to get rid of this and make it a 0. Let me see if I can squeeze this in here. 1, 1, -5 halves, 1 and 2, 0, 1, 3 halves, -2, 1 half, 0, 0, 2, 3, 4, half. Okay. So 1. Let me see here. And let me go. So we'll do we'll do +2 times this row plus this row. So we'll end up with 0 here. +2 times 1 is 2, -2 is 0. +2 times 3 halves is 3. 3 minus 1 will end up giving me a 2. +2 times -2 is 4. -4. -4 plus 7 should be +3. And +2 times 1/2 is 1. 1 plus 3 is 4. Okay, so I'm going to go ahead and copy this onto the next page here. 2, 3, 4, 2, 3, 4. So we have something to continue with. All right. So we've got 1, 1. -5 halves, 1, 2. 0, 1. 3 halves, -2. 1/2. 0, 0, 2, 3, 4. And we have 0, 0, 2, 3, 4. Okay, let's see. What is the best way to handle this one next? Let's go ahead and continue with our process. So now we're dealing with, well, there's a couple of things that we can do here. You notice, so we have a leading entry, we have all zeros in this column, we have a leading entry here, zeros down here, not a 0 up here. So we have a choice. We can go ahead and take care of this 0 and 0 this out now, and then deal with what's left over, the ones that don't have leading entries, or we can go ahead and continue the process and then get leading entries all the way down and then go back and take care of all the other zeros. I think I'm going to go ahead and do that. We're a little bit more consistent with the process that we've done. So now this stays, we leave those 2 alone. Now we're just dealing with this one. So again, we repeat those steps that we did before. 0, 0, this is the first column, non-zero entries, and the first entry is here. So now our pivot is here. And notice we don't have to do anything, we don't have to switch anything, it's already at the top. So since the pivot is there, we can go ahead and divide by 2. So we will divide row 3 by 2 to make it a 1, which turns everything into 1, 1 minus 5 halves, 1 and 2, 0, 1, 3 halves, minus 2, 1/2, 0, 0, 1, 3 halves, and 4 divided by 2 is 2. And then we have 0, 0, 2, 3, 4. Okay, so now I am going to go, this way just to create a little bit more room. What I'm going to do here is I'm going to take minus 2 times this row, add it to this row in order to turn this into a 0. So we'll do minus 2 times the third row plus the fourth row. And what I end up with is 1, 1, minus 5 halves, 1, 2, 0, 1, 3 halves, minus 2, 1 half, 0, 0, 1, 3 halves, 2, 0, 0, when you multiply this out. So minus 2 times that plus that is 0, minus 2 times that plus that, you end up with minus 3 plus 3 is 0, minus 2 times that is minus 4 plus 4, you end up with this matrix right here. So again, we're getting down to where we wanted. We have all zeros down at the bottom, we have leading entries, now we just have to take care of these other zeros to make sure everything else is 0 in the entries that have, in the columns that have leading entries as 1. Okay. So let's see. Let's get rid of this 3 halves first, which means I'm going to take 3 halves, negative 3 halves times this row to this row. So let me write down what it is that I'm doing. So we have minus 3 half times the third row plus the second. And when I do that, I end up with 1, 1, minus 5 halves, 1, 2, 0, 1, 0, minus 17 fourths, minus 5 halves, 0, 0, 1, 3 halves, 2, and of course the bottom one is all zeros. Now I'm going to get rid of this 5 halves. So I'm going to multiply 5 halves times the third row plus the first row. That will give me 1, 1, 0, 19 fourths, 7, 0, 1, 0, minus 17 fourths, minus 5 halves, 0, 0, 1, 3 halves, 2, and of course the final zeros. Now, let's see what we've got. I'm going to create a little bit more space here. This time, I'm going to, so I've taken care of this and this are fine. Now I just have this one to take care of. So I'm going to multiply negative 1 times the second row plus the first row. And when I do that, I get 1, 0. Let me do this one actually specifically. Minus 1 times 1 is minus 1 plus 1, 0. Minus 1 times 0 is 0 plus 0, 0. Minus 1 times negative 17 fourths plus 19 fourths. You end up with 19 fourths plus 17 fourths, 36 fourths, which is 9. And then the same thing here. Minus 1 times 5 halves is 5 halves plus 7. You end up with 19 halves. 0, 1, 0, negative 17 fourths, negative 5 halves. Here you get 0, 0, 1, 3 halves, and 2, 0, 0, 0, 0, 0. This, my friends, is our final reduced row echelon. My apologies for these little marks with a pen here. So the matrix that we started off with, through a series of operations, was converted to this unique reduced row echelon matrix. Okay? This is unique. It's the only matrix that you'll end up with. Notice, we have leading entry 1, all zeros. Leading entry 1, it's to the right of this one, all zeros. Leading entry 1, it's to the right, all zeros. No leading entry, so it doesn't matter what these are. Okay. Let's go ahead and do one more example. We'll move a little bit more quickly this time. Again, we're just doing the same operations that you're accustomed to. Let's take as our matrix 1, 2, 3, 9, 2, negative 1, 1, 8, 3, 0, negative 1, 3. Okay. Look for the first column, not all zeros. That's this one. The first non-zero entry here, our pivot is 1. We don't have to do anything to it. It's already at the top, and we don't have to divide by it. It's already a 1. So all we have to do is turn this into a 0 and this into a 0. So I'm going to do this in 2 steps. Okay, I'll go ahead and let you do what we're going to be doing is multiplying negative 2 times the first row plus the second. Negative 2 times that plus that to turn this into a 0. And the second step we're going to do is negative 3 times the second row. Negative 3 times the first row. Of course, it's the first row. Times the first row plus the third. So negative 3 times that plus that. So I'm going to do it in 2 steps. I'm going to combine it and just give the final matrix that we get. We should end up with 1, 2, 3, 9, 0, negative 5, negative 5, negative 10, 0, negative 6, negative 10, negative 24. So we've taken care of this one. So this is done. Now we want to deal with that. So our pivot here, we look for the first column, that's non-zero entries, that's here. We would look for the first entry from top to bottom, so our new pivot is negative 5. So what we want to do is we want to divide everything in here by that number to turn this into a 1. So we'll go ahead and we have 1, 2, 3, 9. We have 0, 1, negative 5 divided by negative 5, 1, negative 5 divided by 2, and we have 0, negative 6, negative 10, negative 24. Okay, so now let me move up here. I want to get rid of this, make it a 0. I want to make zeros everything underneath. So I'm going to multiply 6 times the second row plus the third. So I end up with the matrix 1. Oops. We don't want too many of these stray marks to confuse us. My apologies. So 1, 2, 3, 9. And then we're going to have 0, 1, 1, 2. And we're going to have 0, 0, negative 4, negative 12. Okay. We find a new pivot. So in this particular case, we've taken care of that. Our new pivot is now negative 4 because this row is done. This row is done. We have leading entries of 1 and 1. We can take care of the others later. We want to work our way down from the top left to the bottom right. We go ahead and divide this by negative 4, the whole thing by negative 4. So let me move on to the next page and rewrite this. So we started off with 1, 2, 3, 9, 0, 1, 1, 2, 0, 0, negative 4, negative 12. Okay. We divide the third by negative 4 to get 1, 2, 3, 9, 0, 1, 1, 2, 0, 0, 1, and 3. So now we have that. And now now we have our 1, we have our 1, we have our 1. We need to convert this to 0, 0, and we need to convert this to 0. So let's go ahead and take, let's do this in a couple of steps. Let's go minus 1 times the third row plus the second. And we'll do minus 3 times the third row. Minus 3 times the third row plus the first. And when we do that, we end up with 1, 2, 0, 0, 0, 1, 0, negative 1, 0, 0, 1, 3. And now what we want to do is we want to get rid of this 2. So we're going to take minus 2 times the second. We're going to add it to the first. And what we're going to end up with is 1, 0, 0, 2, 0, 1, 0, negative 1, 0, 0, 1, 3. Now we check. Leading entry, leading entry, leading entry. Right goes to the right. These are all zeros. These are zeros. These are zeros. No leading entry problems here. This is irrelevant. Our final reduced row echelon matrix is this matrix 1, 0, 0, 2, 0, 1, 0, negative 1, 0, 0, 1, negative 3. That started from our initial one through a series of those operations. Find your pivotal column, find your pivot, move it to the top, divide by the pivot to make it a 1, eliminate all the zeros underneath that 1. Leave that row alone, move down to the next and do the same thing. Find the column that's not all zeros, find the first entry that's not a 0, that's your pivot, move it to the top, divide by it to turn it into a 1, remove all the zeros. Do that all the way down in a stair-step fashion. Echelon is a Greek word for a stair-step, which is why it's like that. It moves in a stair-step from top left to bottom right. And then once you get down to where you can't really go any further, then you go back and you eliminate all the zeros above the 1s to get a unique matrix in reduced row echelon form. Thank you for joining us today at educator.com. I look forward to seeing you next time.